moving on, our next goal basically is to get into what a pre-trained language model is. This means we are going to first talk about better way of tokenizing our input. Remember that so far we have worked with the white space tokenizer and had many issues, some of which I will cover in a second. Next thing that we want to change is to have a better neural architecture. And this is where a big jump is going to happen in this course. So far we have this simple feed-forward neural networks. Then we are going to completely shift into something way more complicated. And that complicated architecture is going to be called transformers. What transformers is going to enable us is to process much longer text. So imagine something like a legal contract where you have many pages of the contract. We want to understand first parts of the contract relative to the last parts, right? And transformer will have this mechanism that which will enable us to understand this long range dependence. Similarly, we don't want to keep doing the bag of words approach where we mix words as if there is no order between them. And although we have dabbled into recurrent neural networks, transformers will also help us with modeling word order. And importantly, it's also going to move us beyond having a single embedding for a single token, regardless of whether this token is polysemous or not, whether it has multiple senses or not. So if I have a word like bank, that can mean financial bank or bank next to river. Now with transformer, we will have a different embedding when depending of the sense of that word we are using in a given context. And then a kind of like another key ingredient is going to be better initialization. I told you that we are approaching our optimization as if it's a convex optimization, but it's not. So we can have all those troubling effects like getting stuck in saddles or local minimas. And what we are going to do, we are going to kind of prime our neural network to be good for many kinds of tasks. And this is going to be called pre-training. And once we have a pre-trained version of our network, we are going to use it for many different applications, from question answering, summarization, translation, and so on. At this point, I'm going to start talking a little bit more about these applications, focusing on both how we approach using LLMs for them, and importantly, how we evaluate them, how we evaluate whether our LLM system is now good at summarization, right? And then we are going to move to other advances of LLMs after that. Okay, so let's start with better tokenization. So just as a setup, remember when you prompt an LLM, you get some response back. And I told you at the very first lecture of this course that the first thing an LLM like ChatGPT will do is tokenize your sentence into tokens. Something we have mentioned many, many times so far in this course. But important difference here is focus on this word superconductors. Here, every color indicates a different token. So I hope you see well that superconduct is an orange token, where ORS is this kind of bluish token. These are two separate tokens. So instead of deeming them as superconductors as a single token, this tokenizer has split it into two separate tokens. And today, we are going to talk about algorithm that can produce that for us. Okay, so we are moving away from the white space tokenizer. As a reminder for why we are moving away from white space tokenizer, a first thing I have told you is that it's not great because it fails for conjunctions, it fails for hyphenated phrases, it fails for punctuation, and so on. I believe someone at Piazza asked, why are these failures? And just to repeat here, you want to separate, let's say, prize winning, prize-winning into three separate tokens, because you can compose word winning with many different words to produce these hyphenated phrases, right? And you don't want to learn every version of this new hyphenated phrase separately, Rather, you can learn price, have a great embedding with its great lexical meaning captured in the embedding of the price, and then by word arithmetic, we can gather and know the meaning of many other phrases, right? So just by decomposing things into units and having amazing representations for the units, you can learn better representation of compositions of those units rather than trying to learn a separate representation for every single composition. Okay, so these were the first problem. Another problem we talked about is what happens when we have something we haven't seen during training, right? Like if we have a completely unseen or a rare word at the test time, what we have to do in your assignments and when we talk about these things is replacing those with unknown tokens. However, now starting to also talk about generative rather than discriminative models, right? We are moving from text classification in generation. We already talked about translation, for example. And LLMs are an example of generative technology, and we are using them very often as chatbots. Now imagine you are writing something to ChatGPT and you get a response with this unknown token. That would be really strange, right? Like that wouldn't be a really nice experience. So for some applications like dial or chatbots, showing unknown tokens is simply not an option. You need to address this in some way. Also, unknown token doesn't have any real meaning, right? So we are basically, by omitting that unknown words, we are almost, whatever that word had said, we are losing that, right? Which is not great. And then in languages with more productive morphology, meaning we can change words to produce many word forms from the same lemma. This is also not a feasible approach because from a single word, from single lemma, you will produce so many word forms that if every single word form becomes an unknown token, you will have simply too many unknown tokens. As an example, I can again use my native language, Croatian, which has 7 cases, which means that depending on how we use a noun, we change it in 7 different ways, depending on its grammatical role in a sentence. And suffixes we use to produce these word forms change depending on the word being plural or singular. So basically you have from a single lemma, you can produce 14 different versions of the word. And now imagine how many words, how many word forms there is, it becomes a lot. And some of these word forms will not be seen as frequently as the others. Okay, so just as a reminder, out of vocabulary means words that we don't see during training. And closed vocabulary model means that these models are not able to produce word forms unseen in training data. All the models we have seen so far have closed vocabulary ones. Okay, so now, we have mentioned a lot of issues with white space tokenizers. So obvious question is, well, what else we can do, right? Like what's our game plan here? And I'm here bringing back a definition of what is a tokenization. Tokenization means splitting a string into a sequence of tokens, and token is a basic unit which need not to be decomposed in subsequent processing as it was defined in ACL 1992. So a long time ago. Tokenization is getting a lot of attention these days due to large language models, but it has been topic for almost as long as I'm alive. So it's an old topic. But the reason why I'm bringing this definition back is this notion of basic units, which do not need to be decomposed further. And many of us here in this room, not everyone, many, come from countries where we speak languages where white space has this nice typographic utility, right? Like it separates words for us in Latin script. But not all languages are like that. So for example, Chinese, here we have 4 different sentences. So just the first example, Yao Ming reaches the finals. And then there can be different ways we can treat characters here. So you can say that the first 2 are making a single word, or you can have basically 5 words where we have these 2 characters kind of mapping to a single word, and two last characters also mapping to a final word. But what researchers have noticed for a language like Chinese, it's simply the best to just ignore words altogether and just work directly with characters. So instead of the basic unit being a word, a basic unit for a language like Chinese is better. The better unit for Chinese is a character. So now we have this conflict. For some languages, we have words being better. For some languages, we have characters maybe being better. But if we would approach modeling English, let's say, with characters, now what is a word is an important concept of language in English language, right? So if we would to use characters in English, your model would need to learn which characters compose a word, right? And that's a lot of extra work for your model. So far, what you need to remember, what is the basic unit? It's not a trivial question. It differs by languages, and we can't just assume that either character or word is better. Now you can say to me, well, Anna, we have a linguistics department here. Why don't we ask linguists what they think with a basic unit of a word? A basic unit of a language should be that we use for splitting strings into. So the challenge is here is that there is among linguists also not a unified definition of what this unit should be. So we can't just reach out to linguists and ask this question because they wouldn't have a simple answer for us. Again, this comes from this variety, differences among languages, differences about even within a language. So what has happened in 2016, and this again is tied to neural machine translation. This has been one of the big advances in neural machine translation together with our attention mechanism and sequence-to-sequence approach. What has happened is that the definition of tokenization has been changed. So tokenization is now a task of segmenting a sentence in non-typographically and non-linguistically motivated units, which are often smaller than classical tokens, words, and are therefore often called subwords. So as in the example I started with superconductors, we have superconduct being one token, and that's actually a word, like a verb, right? But that ORS token, that's not really linguistically motivated or typographically motivated token. Rather, it's maybe a token that you can put to a verb to produce a plural form of a noun connected with that verb. And this has been motivated both with the technical requirements, so observing what I have told you with unknown tokens, and also what I haven't mentioned is if we are using the subwords, our vocabulary is going to be smaller than if we are using full words, because you can imagine now I have 2 tokens, like that ORS being one of them. Now I can produce many nouns, many nouns stemming from a verb by adding ORS token to a lemma, the verb. So there were technical requirements, but also people have observed, for example, in neural machine translation, that the performance improves quite a lot if we are using these subword tokenizers. So now tokenization means tokenizing subwords, And then we are not ditching the white space tokenizer or word level tokenizers altogether. They are going to be called pre-tokens, and the process of tokenizing into words is going to be called pre-tokenization. Now, all of this can seem a little bit pedantic and whatever, who cares? But it's important terminology. So here I'm giving a link to Hugging Face's library, Tokenizer, where you actually have pre-tokenizers implemented, and they're called pre-tokenizers. And now you know, all right, that's referring to, tokenizing into things like words, not something. So it's good to know the distinction between pre-tokenization and tokenization. Okay, and now this is where things get interesting. If we see unseen word, such as, for example, imagine I have seen word low in my data, training data, and I have seen also this token ER, but I have not seen the word lower in the training data, and I observe it during the test time. Now my tokenizer can split it into two tokens, low and ER, and I can use what I know about meaning of the word low and what I know about the meaning of ER, compose it together to understand what the word lower means. Instead of using unknown token and completely ditching the information that low and lower kind of are seemingly related, right? Although we will see also how this can fail later. But this is an important point that now our unseen tokens, we actually process them in a way which is much more meaningful. Okay, is that clear? Oh, go ahead.
I'm just thinking about the term pre-tokenization with the old way tokenization was done with things like separating into words.
Mm-hmm.
With being called pre-tokenization, does that imply that for processing's sake, it may be helpful to do that pre-tokenization first before moving into this new Subword tokenization?
That's right. Yeah. So you're basically first, you take your corpus, which is just a bunch of written texts, which are basically strings. You're first pre-tokenizing them into lists of words, let's say, if pre-tokens is a word. And then given that, now you're going to do the subword tokenization over the list of words.
Okay, that makes sense.
And it's going to become clear how when we go over the BPE album. Okay, so let me just write here, not to forget. I want to come back to the points that the size of the vocabulary. So size of the vocab is going to be smaller. Once we go over BPE, I'm going to cover that again. And don't forget that another benefit is unseen tokens are now processed in a way that's meaningful. Okay, so before I go into and tell you how we can go about Subword tokenization, I just want to go over a little bit of more of terminology that's important to know. So morpheme is the smallest meaning bearing unit of language. So for example, in the word unlikeliest has the three morphemes. It's going to be unlikely and EST. And what you will see with subword tokenization is very often subwords look like morphemes, but they're not always it. Okay, so very often, but not always something like morphemes. And morphology is the study of the way words are built up from morphemes. Word forms, as I mentioned with the case of Croatian, basically are the variations of words that express different grammatical concepts. So, for example, we change, even in English, we change words, but depending on whether something happened in past or future. This is not so important for English because English has mostly lost its inflected case system, but for many other languages, you change nouns and pronouns based on their relationship with other words and their grammatical rules. As I mentioned, like you can change a single noun in 14 different ways in Croatian. Singular, plural, also in English, and then also not extensively used in English, but in many other languages, every word gets its gender. In Croatian, for example, is going to be nice, at least because depending on the suffix of a word, you know what its gender is. So, for example, words that end with A are often feminine. I also had to learn German, and there you mostly need to learn the gender, which is another piece of information to learn when you're learning a single word. I don't know, have you seen SNL sketch with Bad Bunny last week about like gendered words in Spanish? This kind of nicely shows how it kind of doesn't make sense which words are feminine or masculine. But in any case, you will get different word forms based on that. Okay, and then just to repeat, subwords can be arbitrary substrings, but they can also be these meaning-bearing units, such as morphemes EST or ER. Okay, right. Now our goal is to learn one way we can tokenize text into subwords, and we are going to use BPE tokenizer for that. Okay, so everything I say now is super important. BPE is used to this date for your favorite large language models. So it is a very modern algorithm, or I should say usage of this algorithm is happening to this date. And what is important to know is that with BPE, we are going to learn what are the tokens we should add into our vocabulary in a data-driven way. So unlike previously, where we split the sentence by white space and we said wherever is remains is going to be the token, now the tokens are going to be learned from a large corpus, which is quite interesting, I would say. And I should also mention here, when I say that BPE's history stems from a long way back, all the way to 1994, because this is basically a compression algorithm. It only happens that in 2016, it was applied to neural machine translation as a way to tokenize text. Now, what's the connection between compression and tokenization? The idea is that BPE is going to find a minimal number of tokens that compress your data. That's the idea between how compression connects to the tokenization here. Okay, so when we say BPE, we actually mean two sub-algorithms. One of them is token learner or trainer. That's a part of all algorithm which will get a raw corpus, so just written text. And from that written text, we are going to produce a vocabulary. Okay, so visualize it a little bit, have corpus, right? Sentences. From there, we are going to get the vocabulary where we have our tokens. Token 1, token 2, and so on. Now, once you have that, you are going to also have a part of your algorithm which is going to actually do the tokenization part. That's called token segmenter or encoder in literature. So here, after this, we will get any sentence, and we are going to tokenize it into a list of tokens. And these tokens are those that come from the vocab. Okay, so now I'm going to go over how we do this part, and then how we're going to do this part. Full disclosure, this is going to be your next assignment. You're going to implement BPE. So if you need extra motivation to listen what's next, I would recommend paying attention now. I am fixing parts of the assignment. It should be released today. And I know you have only a few days to do it. I fully acknowledge that. It's written in a way that you shouldn't need as much time as you needed for the first or the second assignment. But let me know if it gets a bit busy for you, and I will consider that for the prep. Okay, any questions before we move forward with how to do the token learner? Okay, I will give you an overview step by step, and then we are going to run it on an example, okay? So with the token learner, we are going to get some training corpus, and our goal is to produce a vocabulary. The first thing we are going to do is pre-tokenize the corpus into words and prepend a special start of word symbol for every word that's not the first word in the document, like underscore or this weird G. The reason why we prepend this start of word tokens, special tokens, is basically comes from the classical implementation of this algorithm, where you take your word and you're going to add white spaces between each character for implementation reasons. And then you want to signal the difference between the actual white space in text and the white space you added for the implementation reasons. So you need that little detail. Then you're going to initialize your vocabulary with a set of tokens. So we are starting with a vocab here that's going to be all characters that have appeared in text you given to the algorithm. So if it's an enormous language, English language corpus, you can assume the vocab, starting vocab will basically be all the characters in English alphabet. These days we do multilingual pre-training, so we'll have languages, many languages, 100 languages, and they are going to come from different scripts. So the initial set of characters will be richer and will contain characters in different alphabets. Then basically what BP does is going to merge it's going to find two tokens in your vocabulary that most frequently occur together. And then it's going to merge those two most frequent tokens into a single token. We're going to add that new token to the vocab, and we are going to replace all occurrences of these two tokens with this new merge signal. Okay, so that means choose two tokens that are more frequently adjacent. And because we are going to keep adding these merge tokens in the vocab, it's important to notice that here I'm intentionally using tokens rather than characters, right? Whatever we get as a new merge symbol, we are going to add to the vocabulary, and then in our corpus that we are working with, we are going to change the occurrences of these two selected tokens with a new merge token in each word separately. So now in each word separately, I kind of emphasize it here. And the reason is that we don't want to merge tokens that go beyond the word boundaries, right? Like we want to respect the word boundary. And this is why we do the pre-tokenization, right? So first we are like, okay, these are the words, but let's see what should we break up these words further? But we don't want to merge things that don't belong to the same word. So for example, I'm trying to think of an example on the fly. I had the word hello. And then there's white space and world. Oh, perfect. Then LOV, if I have decided that's going to be a token in my vocab, I ignore that there is a white space here, and I'm like, okay, there are these three together. That would mean that I would then, in the next step, merge these, which would merge these two words together. So we need to respect these boundaries. Okay, and now here is a hyperparameter. As always, that has to be at least one. We're going to basically repeat this process until we do k merges, which also means that our final vocab size will be of the size of the number of characters we started with plus k. Because with k merges, we are going to add k new tokens in the vocab. Okay. As always, you can ask what's the appropriate k, and that, as many times as I tell you, either your choice or an open research problem. I highly recommend reading this survey I'm linking here in general, but there is a whole section of you know, what are reasonable k's. In these LLMs, almost to this day, very often you will see value of 30,000 as a number of as the size of the vocab, so approximately this the number of merges we do. Now let's just check for a moment. Why is the size of vocab important? What can happen if I set the size of vocabulary to be too large? Let's say I choose it to be 1 million. Like, which part of neural architecture the size of the vocab is affecting? Let's think about matrices in the architecture we have defined so far. When do we use the vocab size? Yes, we do.
The size of the final output matrix.
Yeah, exactly. The final matrix, which determines the distribution over the vocab. The matrix is of the size of the vocabulary times the dimensionality of our inner representations, right? So if I have enormous value for my vocabulary, like 1 million, and dimensionality is very often like thousands or more, oh boy, I get a lot of numbers, right? Just in that piece of my architecture. Then remember, each one of these numbers, if I keep it in 32-bit precision, which I would very much like, that requires a lot of memory to store all these values, right? And I also want to train this on GPUs, and the best GPUs are going to be bounded by 100-something gigabytes of memory. And previously, that was a dream to have this many gigabytes we have today, but it's still constrained, right? Like, we can't fit whatever we want. So you don't want enormous vocabulary size because you basically don't have hardware to keep such a huge output there. Which is a point that I also wanted to bring as a point one here. When we work with words, we needed more tokens because we never had a chance to represent a word form with a composition of 2 tokens. Now, every single plural form of a word, I can have as a you know word plus its s in English language, right? So bunch of plural forms of a word I can represent with 2 tokens that I have in the vocab, which then reduces the vocab size. Does this make sense? Okay. Okay, let's go over an example. So I'm showing you how to train token learner or trainer of BPE. The first step is going to be pre-tokenization. Just because I know I'm leaving. Do we need a break before we go into this? Not really? Okay, let's go into this then. So we are going to split our input. So for example, here I have a document which is very short, and I'm going to mark word boundaries. So I'm going to mark word boundaries of all words that are preceded by white space. And here I'm using this very weird looking G. This is not my random funny choice. This choice comes from the actual implementation in Hugging Face, which is the state-of-the-art implementation of BPE. So in front of every word that has been preceded, that is following the white space, you add this special symbol. And the reason is basically this. So the way this is very often implemented is, and you can have different ideas, but I want to explain you why you will see these weird looking G's. The reason is that every token from the pre-tokenization is going to be represented in this way, where you have a white space before the character. Okay, so we have hello turning into hello, where we have a white space in front of each of the non-starting characters. And if I had white space here, then I would mix this white space that I have introduced for my quotation with real white spaces. So in this way, you have this weird looking symbol, which kind of is a placeholder for this was a real white space before. Okay, so first I do all of that. And then, as I said, I'm going to initialize vocabulary with a set of all individual characters I have observed in my data. So from these words I have observed these characters, okay? And notice, because my document is really short, this is not all of the words in English alphabet. If my corpus is much larger, which it's gonna be in the real application, then here you would have basically entirety of the alphabet. And that's important because if I, as I said, and I will come back to this, I said that even if I haven't seen a word at the test time, that I haven't seen it during the training time, something that I see at the test time, I will always have a way to represent it. And the way I can always represent it is with so-called character fallback, basically representing a word just as a sequence of characters in it, as long as those characters are part of the initial vocab, which very often they are. Okay, now I need to find two tokens in the current vocabulary that are most frequently adjacent. So basically, I'm checking pairs of the tokens. Remember tokens here. And I should go back here and emphasize that the whole process of PPE is going to extend this vocabulary, right? As we are doing these merges, we are adding something to the vocab, right? So this is just going to become bigger vocab. So it's important that we use this terminology token, because next time I'm doing a merging operation, I will have one of those merge symbols as my token, right? And that's not a character anymore. Okay, but in the first merging operations, basically, we are looking at all the adjacent tokens, which are so far only characters, and we are looking for the one which is the most frequent pair. Here we have something that's going to happen often, which is basically have three of them having the same frequency, so you just randomly sample one of them as the most frequent. Okay, so here I believe I chosen OR. That's the most frequent one. And now I need to, in my data, replace all occurrences of the original background, which is OR with this weird white space between them, with my replacement, which is OR without white space, right? So now it's going to become its own thing. And this is where you might getting a sense of why adding those white spaces was useful, right? Because it kind of tells me, okay, what is separated here, right? And then in Python, I can just use split to split it by white space. Okay, so in all of the words except the third one, we don't actually have occurrences of OR, only the third one we have, and here we replace it by OR, which is merge without white space. Okay, so this is what we have done here. And then importantly, we are also going to record which merges we have done. So we are going to, in some, let's say, list, we are going to add that we have merged OR together into OR. And this is crucial because later when we go to our, actual tokenization, the way we are going to do it is by applying these merges to our piece of text that's basically looking something like this. So basically this part where we are changing these separated symbols with the merge versions is how we are going to do tokenization later on. So we need to record which merges we have done, and then later we are going to apply them greedily in order we have collected them. Okay, and then of course, important bit is to now extend our vocabulary by this newly defined token OR. Is this clear? It's a little bit boring, right? But it is how this algorithm works, right? Okay. Now, once I have done this, I'm going to repeat all of that k times, 30,000 times. I'm going to go back to the point where I need to collect which pairs of tokens are the most frequently adjacent. And now I will have that special token OR, which might be coming with another token most frequently together. And then I'm going to again do the replacement of whatever was the most frequently occurring pair of tokens with their merge version in our data, record the merge operation, append more stuff to my vocabulary, and then go back to collecting pairs, then replacing the most frequent pair with the merge symbol in the data, recording the merge operation, extending the vocab, and so on. So I'm just going to repeat that many, many times. Okay? Yes.
So I'm guessing given the different corpus, like the vocab doesn't change like between one corpus to the next if they're sufficiently large too much, I'm guessing. But the corpus itself will dictate the embeddings that we learn quite a bit.
Okay, that's a great distinction which you're mentioning. So first, I would disagree that if I have same tokenizer but two corpora, that I will get same vocabulary. It really depends on how similar this corpora is. It needs to be highly similar for my vocabulary to look the same. And actually, because different LLMs like GPT has this tokenizer, Roberta has this tokenizer, Gemini has that tokenizer, we can't do comparisons between these models, the level of control we would actually like, right? So their vocabulary differs, blah, 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 everything, right? So different corpora, as soon as you have different corpora, I would say your vocabulary might look different. Of course, if the difference is non-negligible, maybe then no, right? But then you mentioned something else which is interesting. So now we know in this whole course that once we have defined the vocabulary, we are basically going to represent each token in the vocab with an embedding. And we are going to continue doing that. But the corpus we use for training the model and therefore the token embeddings can be quite different. And this is why we are going to have something called glitch tokens that I'm going to mention hopefully at the end of today's lecture. Maybe I can actually jump into it and come back. Oh no, I hopefully didn't break this. Did you watch the movie Eddington? It was released recently. Anyone? Nice. Okay. Did you like it? Yeah. Not super.
It was crazy.
Not super convincing. I'm not sure whether I liked it. But anyway, in this movie, so I'm watching the movie and I'm like, no way. Like there is this token called solid gold Maggie Kerp, which is one of the first examples of these glitch tokens that have been introduced in the field. And the director here has used it as a metaphor for this corporation that's kind of central to the movie, but hidden. And these kind of glitch tokens occur exactly for the reason we are talking about right now. We have a corpus we use for training our Subword tokenizer, and then we have corpus that we use for training the LLM. And if imagine these corpora are not exactly the same, what can happen is that your tokenizer learns that certain thing must be its own token. So for example, in this, I don't know when this was noticed first time, I would say 2023, it was noticed that this token solid gold Maggie Carp is a token in the VOCA, like a full-on token, single token. And it most likely appeared because a lot of data we use comes from Reddit. So if you have this different combination of words appearing together, something like this will come together. Or some other glitch token is a username that has been frequently used, and so on. So now you move to the training a model with another corpus, and you never see this token because it's such a weird token that has been produced from some peculiar thing specific to the data you have used for training your Subword tokenizer. And because it doesn't occur often in the training data of the model has no chance to learn to good token embedding for it. And now what happens in practice is because it doesn't have a good token embedding for it, the model starts to produce really weird behavior, such as in this particular case, it's doing this odd redirecting where basically assumes this word means distribute. And then you prompt it by using this token, and you wouldn't expect anything meaningful coming out of it, but it starts to talk about distributing some. In some other glitch tokens, you will see refusing to output a token. So I think someone's name was, no matter how hard you try, you wouldn't get the model to actually mention their name, or you can get just unpredictable behaviors. And then people have observed, oh, if that's happening, I can maybe use these glitch tokens as a way to do something bad with these models and use it as a backdoor. So it has safety connotations. But yeah, that's a great point. So the data we use for the tokenization and data that we use for corpus, at least at that stage of our LLM's lives, have not been entirely the same. And then it resulted in these glitch tokens. Okay, but let's move on here. Okay, so after we have trained our token learner, we have collected vocabulary, right? And also these merges, these merge operations. I would think just about them as a list of symbols or tokens that you have merged together. And now when you need to actually do the tokenization, what you are doing is you're just running that merging operation we have done at each iteration of BPE now on this new sequence you give it. So basically, you're first going to segment the sentence into characters, like we did, we did it in a way where we put those white spaces in between each character. And then you are going to apply merging rules in an order you have collected them. So you greedily apply them. First merge operation you have ever recorded, you're going to apply that one first, and so on. So it needs to be in the order we have given to the model. So you're going to apply the first operation. So imagine we have, initially characters T and R, and our first merging operation we have done was to combine ER. You are going to put them together, and they are going to be now joined to and so on. So eventually, you're going to end up with a string which has some white spaces in between, and then you can just Python split it, and you are going to get your tokenized list, right? So that's it. The core part of the algorithm was actually to learn the vocabulary and the merging operations. Yeah.
If we're doing this greedy search for our merge rules, then theoretically, if the order of words in the corpus were changed, could that potentially change what is the first merge rule?
I don't think so, because it's not about the order they appear in, is that how often they appear together, right? So if they all appear really, really often together at the beginning of a corpus or at the end of the corpus, it doesn't matter.
What about the case of ties, like how like in the Hello World World Peace example, there were multiple cases of, two parent ties.
Just randomly pick one. Yeah. Whenever we have a choice, the best is to randomly do it because randomness beats any kind of decisions. Very, yeah, not very intelligent, but it works really well. Yes,
So
please.
that test time, we taken the sentence, we split it into characters with a white space between each character. Then we apply all our merges, so it removes some of the spaces,
Yeah.
and then we split it, and that gives our final tokenized.
Yeah, I believe I have an example. So here, yeah, imagine my merges for OR together and OR and L. So these are, just imagine like a little toy example. These are the merges I have collected during my token learner. And imagine my input is just a single word called world. Why did I do this to myself? These are two similar words. First thing, you split it into characters, and basically what you do if you want to like really hint into like how to implement this is you are going to iterate over the positions in the so far tokenized word text. So right now my tokenization is what I'm showing you here, right? This is my current tokenization, and then I'm changing the tokenization. So what you do is in your current tokenization, you look into the first position, which is this weird symbol, and you check whether this position has O and the next position has R in it. And you see, well, it doesn't, so I'm going to move forward. So you move to the position 1. You see here is on the position 1, do I have a word O? No, I don't have, so I can move forward. Then in the third iteration, I'm like at the position 3 or 0, depending how you see it, is now in this position. Do I have word O? I do, right? And in the next position, I have word R, right? Great. So what I'm going to do, I'm going to replace these two positions with a single token, which is going to be OR. And I'm going to basically jump in my first copy in 2 positions per. And that's it. You're kind of keep doing that. The next 2 positions won't have a special OR token, so I'm not gonna replace them by the merge symbol. And you would do this for every single merge operation. Here, I visualize how you would do it only for a single merge OR. Imagine this is the end. This is what we got by applying all of the merge operation. Imagine this is the list we got. This is your ultimate tokenized list, right? So this is the tokenization if I had applied all of the merges, and this is what I got. I know it's a bit strange, but that's how it works, right? Is that clear? I just want to see that it's not confusing. Okay. So I also want to mention that this weird G was always this placeholder for white space. So because we know that we are not using tokens only to tokenize input and represent them by embeddings, we also know that if we are doing text generation, we are producing indices that are corresponding to tokens in the vocabulary. So if you have this weird G in a token that you want to show to a user, of course, you don't want them to see this weird looking G's. So those are the ones you replace by white space, and then you can join the entire string and display it back. So just don't remember that weird looking G, basically a placeholder for white space. Okay, now I want to show you a few more things. Okay, there it is. Let me just. All right, so have I ever told you about Hugging Face so far? I haven't much, right? Okay, so if you are working with an open source NLP or LLMs or AI in general, you will be using Hugging Faces and ecosystem. It's a really weird name for a company that's tremendously important. Okay. All right, we are gonna hope this works. So Hugging Face has important libraries that you're gonna be using if you continue working in this space. Most important one is transformers, which will become clearer when we explain transformers in a next lecture. But if you wanna basically use a pre-trained model, all the weights of these models and all the code you need to work with them, it's in Hugging Face. Then they have a library for datasets, which enables you to load data sets in a really easy way. You don't need to do scripts for loading the data. And they also have a library for tokenizers, where you have all of these algorithms for Subword tokenization implemented. And if you need to train a tokenizer, although you're gonna do it in your homework, and I'm sure it's gonna be amazing, you can still use these versions that exist in these libraries. So I just want to show you how easy that becomes if I can make this work. If not, I'll just share it with you and you will run it at home. All right. Let's see. Okay, seems like it's working. Okay, so basically you pip install tokenizers, the library, and then from tokenizers.models, you can instantiate a version of the class BP tokenizer. And then you can do your white space tokenization by loading a white space tokenizer. It's a little bit overkill for, white space tokenization. It's pretty simple. But for example, here, let me see. Yeah, so here you have a tokenized version of hello, you all, how are you? With a sick emoji. I don't know why there's a sick emoji here. In any case, probably someone wrote this in pandemic. But here you also have, if you need basically character positions in the original string. And this is useful when, if I give you a corpus that's already tokenized, sometimes you want to have like original version of that corpus, which it was not tokenized, and without knowing which pre-processing decisions, etc., you have done, it becomes really hard to work with the just tokenized version of a corpus. So libraries will have these features where they give you offsets of the characters producing the corresponding word. And now, this is actually amazing. They have written this algorithm in a quite efficient way. So you can load the BPE trainer. You can set the number of merges to be, I actually don't know how many merges there are here. I don't think the batch size refers to the number of merges. But what I want to emphasize is that we are taking the wiki text corpus, which is basically a dump of Wikipedia, and on it, on the raw version of it, we are now training the BPE, and this will be done in a matter of a few minutes. So it's super fast. And this is a reason you might want to use their versions of these algorithms, because they're very often written in a way which is very, very, very efficient. So if you ever need to train a BP tokenizer, you can easily use this library. Okay, and once it's trained, this is how, once we have trained this BP tokenizer with Hugging Face, then the producing tokenization is now AGL will be one token, LO, comma, I, and so on. What are the things you like about this tokenization, this resulting tokenization? I can notice few things I like. And similarly, what is the thing you potentially don't like?
Numbers are split, so one number is split, yeah, which could be a problem.
Yeah. This, not good, right? And this is actually the reason why these models, LLMs, are not great at mathematical reasoning, among other things. But this is one of the huge things, that numbers get split into this weird way. And you would not deem this number here to be needing to be split, especially not like this. If anything, you would split it in 17 to kind of signal 17,000 and then the rest, right? One thing I like is we get this nice separation and punctuation is split actually, right? Unlike with our full white space tokenizer. Okay, so let me just finish with a few more thoughts. I'm giving you here some resources. OpenAI doesn't release anything, but they do have a library for their tokenizers, so you can check that. It's called TikToken, very cute. I also recommend the Hugging Faces resources. You have a notebook, you have so much to work with. And then Andrei Karpati has his own nice mini BPE library. Give me just 1 minute. We have 1 minute left to wrap tokenization. I taught you BPE, and although it is super used to this day, there are many other tokenization algorithms, and it's a very active area of research because tokenizers are to blame for many of the issues we have with LLMs. And at least it's an endless source of our meme game, which is good, but at the same time, it's causing many issues that Andrei had really nicely summarized in his video. So I welcome you to look at that, video. I highly recommend it. And just as one example, I want to mention how to this date, the Subword tokenization, although it have given us many benefits, it's also given us a lot of problems. Here is an example of sentiment classification where we use Subword tokenization, and then super bizarre, which has kind of maybe negative connotation in the context of a movie review, has been split into Superb and then these other tokens. And Superb itself has a really positive connotation, right? So now the model had made mistake just because of the tokenization issue. You have mentioned the mathematical problems we have seen. That's tokenization is a major reason. And also when we started to do LLMs for coding, white space, how we, for example, use certain number of white spaces to indent our code, that has caused issues because the tokenizer would split it into many white spaces, whereas it would be nicer if we had, one token for 4 or 8 white spaces. And just introducing those tokens had improved the performance on code comprehension quite a lot. So again, I can go on and on the various ways that tokenization can lead into downstream issues. Andrei has really nicely summarized them. So please check that out. All right, thank you so much. Sorry for taking a bit more time.